I from 1 to n, bi minus ai. Okay, so this is the sum of the lengths of all disjoint, undisjoint open subintervals on AB. Okay, so whenever the sum is less than delta. Okay, so this is called F's continuity. Right, so that you can see here A, B, right, and then you can make you can select disjoint open subintervals. So we may select C here. Okay, so this is A1, this is B1, A2, B2, and then maybe we select AN, BN. Alright, so they are disjoint. Here we have n disjoint open interval, and the length, the sum of those lengths. So okay, so that have sorry, this is so the length of the first open interval is B1 minus A1, right? The length of the second open interval is B2 minus A2, etc. So if the sum of lengths of this open interval is less than delta, right? Then the sum of the absolute value of the difference of function values will be less than epsilon. Okay, so that so you say here, okay, and then the corresponding. So up here. So this is f of B1. This is f of A1, f of B1 here, and okay, this is f of A2, f of B2, etc. Okay, so that, and so this is the definition of absolute continuous function. Okay? And this one implies continuity. Why? Well, you can see that continuity corresponding to only one subintervals. Okay, so if OI and BI are near enough, then the function value will be close enough. Okay, so this is the and you can see that it is a uniform continuous, right? Because that by our definition of uniform continuity, you can see that the sigma and delta does not depends on. So given an epsilon, okay, and the delta selected, well, independent of x, right? So in any x in the interval, okay, so that, okay. So this is implies that for all epsilon is 0, the x delta is 0 such that f of x minus f of y less than epsilon for all x minus y is cross theta for all x, y in AB. Alright? Which that is f is uniformly continuous on AB. Okay, and so this is implies that f is continuous on AB. Okay, so absolutely continuous functions must be uniformly continuous functions. Okay, so this is a very, very strong condition. Okay, right. So the full conditions. Okay, and the absolute continuity implies that the second derivative exists for almost all points on AB. Okay, so this is the result in analysis. Okay. Okay. So this is our remark. Now the set of all functions satisfying these four conditions. Okay. It can be verified that V is a vector subspace of the L2 space. Okay, so it's a vector subspace. Now we define a linear transformation L from V, from this vector subspace to the L2 space. Okay, in the form, the L, okay, will transform U. U is a function in capital V, in the following way: 1 divided by x minus p of x u prime minus q of x and u. Yep, okay. So for each u in V, you compute this function. Okay, and this function must be in L2. Okay, must be in L2 here. Okay, so this is for all u in V. Okay, and which is called, so this is a linear operator. Okay, it's called regular. It's called a regular string Liouville operator. Okay, associated with the regular standard Liouville problem. 1.5.3. Okay? In here. Okay? Okay, so in this case, so when we define the linear operator L, linear transformation, I'm sorry. When we define linear transformation like that, a regular stem linear problem on AB becomes the following eigenvalue problem. Okay, is L U equal to lambda U. Okay, the vector space V. Okay, so this is become to the eigenvalue problem. Okay, so you can look back. Why this is? Well, when we see here. This is our regular stem linear problem. Okay, so that from the regular stem linear equation. So initially we have it here. Okay, right here we have. Now we have R and the Rx, y. So we move this one to pair of x, y prime, and the prime. Okay, prime, and minus q of x, y. Together, right? And then lambda y becomes to 1 over Rx and minus p of x y prime minus q of x y. Okay, and this is it's just y here. Okay, so as you can see, the eigenvalue problem, because this is the linear transformation, right? L, okay, and U give us lambda U here. Okay, so we want to find non-trivial solutions for this eigenvalue problem. Okay, we want U to be non-zero. Okay, and for any such U will be called an eigenfunction. Okay. Eigenfunction, and the corresponding eigenvalue, lambda will be called the corresponding eigenvalue here. Okay, so the eigen problem will be the same as the regular standard equation here. Okay, but in our construction of capital V, we know that U should be in V. And we know any U and V satisfy separated boundary conditions. Okay, so this is automatically in all construction. Alright, so that we should know that U is in capital V and so U has satisfied these three conditions, especially if you satisfy the two separated boundary conditions. And because the first three tell us that U as a candidate solution of these differential equations, we know that the solution we should have a derivative, and we ask for the derivative is absolutely continuous. Okay, we have a stronger condition on the continuity of E prime to make sure that the second derivative exists for almost all the points. And in that case, we also ask that the second derivative is in L2. Okay, it's in L2. Okay, so that's this. And so now we will give an important theorem in this section. Okay, a regular Stern-Liouville operator L is self-adjoint on V. Okay, with respect to the leading function. Of X, i.e., what do we mean self-adjoint? For all U, V in capital V, we operate on U, okay? And so we know U, by definition, is in U2, okay? Right, and so we take the inner product with respect to the weighting function R, so this way, alright, and take the inner product here. And this one is equal to U, but U here, but we take the we act the linear, this operator, the L on V instead. Okay, this is called a self-adjoint. Okay. So that when you consider this kind of inner product, okay, the same as this inner product. Okay, so you can apply the regular Stern-Liouville operator L on U or here on V. Okay, and they are equal. i.e., AB R of X and L of U. Okay, and V bar dx, so L of U and then X Vx bar dx. So this is the inner product here, equal to AB Rx U bar dx and dx here. Okay. So we must have so the inner product. So we have so that the operator L is self-adjoint, means that we have this property. We have this property there. give a proof. Now, since when we evaluate this integral, then, okay, and we plug in this one, so x times u becomes to this one. Okay, so we have two terms here. We have two terms. Okay, so we have minus ab p of x u prime of x prime. Alright, and vx bar dx minus ab q of x u of x and vx bar and dx. We have that. Okay, and so now we have it so that by integration by parts, we know that so we know the product so by integration by parts here, we have minus p of x, u prime of x, times vx bar from a to b, okay, plus a to b, and minus minus becomes plus, that's why, minus, and minus p of x, u prime of x, okay, yeah, and the derivative, so x, the derivative of the bar, okay, dx, so this is from integration by parts, alright, and here we have ab, q of x, u of x, v of x bar dx. Okay, so this is by integration by parts. Right, so this is the first the integral on the left hand side, and on the right hand side we can ab x and ux v x bar dx, okay, and this is equal to minus, okay, ab ux, so we multiply x with this one, okay, so you get p of x, and okay, we prime of x prime, okay, dx minus ab ux qx and the vx bar dx here. Okay, and now that the p is always positive. Okay, in our regular problem, so p is always positive. Okay, And if we take the bar, we have U bar prime. And again, by integration by parts, we have the minus Ux and P of x, x here, and AV. Okay. Minus AV and U prime of x minus P of x V bar prime of x dx minus AV Q of x E of x and V of x bar dx. Okay? So you can see, again, here is again by integration by parts. Okay, now we take the difference, alright, of the two integral. So AB x U Vx bar dx minus AB x and Ux V x bar dx. Okay. Now you can see that when we look at that, we will see they can cancel, right? Because this is the same term. You cancel, and the middle term, you have the same middle term here. You can cancel them, right? Okay. So that this becomes to that. Comes to P of x. So P of x on both sides, yes. And U of x, V prime bar x minus U prime x, okay, and Vx bar here. Alright, from A to B. Okay, so we have this one. Alright, P of x and Ux V prime x. Okay. We can write this way. V prime of x bar. Alright. Okay, and this one. So this one, okay, which is called the Lagrange's identity. Lagrange's identity. Okay, we have that. Now, by the two boundary conditions, okay, in the 1.4.3, we have this one here, so that we have that, UA, okay, and U prime A, and we have V A bar, V prime A bar. This is for K1, K2 is equal to 0, 0. And So this is at the point endpoint A. At endpoint B, we have UB and U prime B and VB bar, V prime B bar, and L1, L2 equal to 0, 0. Okay? Okay, look here. Now, as we know, at least the rank of K and K2 means 0. So that this system equation has what? Has non-trivial solutions. Okay. So since both linear systems have non-trivial solutions, K1, K2, and L1, L2, respectively. Alright? Now, so the determinant of the determinant of this matrix must be equal to 0, and the determinant of U B, U prime B, V B bar, V prime B bar, also 0. Why? Because when this matrix is invertible, then we have only trivial solution, so which is a contradiction. And so this one must be non-invertible. When this is non-invertible, it means that the determinant is 0. Okay, so we have that. And so that we know that this says that UA, V prime A bar minus U prime A, and VA bar should be equal to 0. And here, UB, V prime B bar minus U prime B, VB bar is 0. Okay? So we see here that when we put B here, B, UB, V prime B bar minus UB, U prime B times VB bar, this is right here, this is 0. Okay? This is 0. And when we substitute A here, okay, we got this is 0. Okay? So that this implies that the P of X and Ux V prime X bar minus Ux V prime X and Vx bar A to V must be equal to 0 here. Okay, so this is 0. And so the left-hand side of Lagrange identity is equal to 0. I'm sorry, the right-hand side. The right-hand side of the Lagrange identity is 0. So this is right-hand side is 0. Alright, so that the right-hand side, the difference is 0. And so that will be equal to here, right? So this proof that the Wittgenstein neural operator L is the self of the joint. Okay, so this is, so we have this one. Alright, so this is an important theorem right, to be used. Okay. Alright, so I'll stop here, and we will have quiz exam next Monday. Alright. Okay. So I will assign next recommended exercise soon for you to study to prepare for the next quiz. Okay. So see you next Tuesday.